Overview: Algorithms to Live by Brian Christian and Tom Griffiths is an immersive look at the history and development of several algorithms used to solve computer science problems. It also considers potential applications of algorithms in human life, including memory storage and network communication. One such computer science problem is the optimal stopping problem, the mathematical puzzle for determining how long to review options and gather data before settling on the best choice available. The algorithm, based on statistical analysis, shows that there is an optimal place or time to stop researching options or solutions to a problem and instead commit to the next option that's just as good as those already considered. Similarly, the mathematical way to decide whether to try something new or stick with the familiar choice is expressed by the Gittins Index score of any given alternative. It values a complete unknown more highly than a choice that has proven to be disappointing once or twice in the past, depending on how many times that choice had a positive outcome. When planning the schedule for a single machine or person, the order of tasks should depend on whether the goal is to achieve deadlines or to minimize the time a task remains undone. However, once tasks that rely on each other to be completed are introduced, the algorithm becomes too complex for a computer to solve. Problems like creating the shortest possible route between a long list of destinations are too complex for even computers to solve in a reasonable amount of time. But creating a version of the problem with less complexity, where rules are relaxed or where rule breaking is only slightly penalized, can lead to near-perfect solutions. Randomness can be used to test theories to a high degree of probability, but the benefits of speed and reduced computing power offered by the use of random sampling come with a trade-off of certainty. Randomness also introduces changes that can push a system toward a more desired outcome. This can occur when someone has an inspiration or when randomness is used to push the model away from a deceptively attractive yet suboptimal solution. Algorithms also apply to game theory. Opponents often play a game on multiple levels and can choose between cooperative or competitive play styles. Game theory calculates a price of anarchy, the change of potential outcomes between cooperative and competitive play. Changing the game's rules, introducing emotional factors, or creating information imbalances can encourage the equilibrium to move toward cooperative or competitive play. With a more nuanced understanding of decision-making, society would be improved by making decisions easier for members through computational kindness, the practice of which can reduce the complexity of the many algorithms needed in the search for an optimal solution.